Hi everyone, I'd like to tell you about Lévy's downwards theorem, which will pave the way for proving the strong law of large numbers. Suppose we have a probability space, as usual, and on it we also have, so on this probability space, suppose that we have kind of a reverse filtration, G of minus n sigma algebras with the following property. So first of all, n will be indexed on positives, so this will be g minus 1, g minus 2, g minus 3 and so on, and the property is the usual except that the indices are negative, so it's an increasing system of sigma algebras as the indices themselves increase, but if n increases, then this is going to be a decreasing system. Okay, g minus 1, and also define g of minus infinity as the intersection of these. Okay, so as n increases, then we're going back and back in this line. So we're going to rougher and rougher sigma algebras. It's in a sense decreasing in some sense. It's getting rougher and rougher. And then the limit, the natural limit we want to define here is going to be the intersection of these sigma algebras. That's g of minus infinity. Now take a random variable gamma in L1 in this probability space. Okay, and define m of minus n, this quantity, as the expectation of that gamma, conditioned on g minus n. Then the theorem is that this thing is a martingale. M of minus n is a martingale. Well, okay, let's do it this way. M of k. Let's use k here. M of k, I'm using k for minus n, is a martingale. M of k is a martingale. M of minus infinity as the limit as k goes to infinity. Well, n goes to infinity. There is always this ambiguity of whether using minus n or plus k. Okay, so as we're looking at more and more negative indices, then this limit will exist almost surely, and in L1. Okay, and guess what? M minus infinity, this limit is going to be equal to the expectation of gamma given g of minus infinity, almost surely. Okay, so that's the theorem, right? So you could imagine this as kind of going backwards in time, and g of minus n is all information contained up to time minus n. So it's actually in some sense the usual way of defining filtration, except that the indices are going backwards, and I'm interested in the backward limit of this whole system. So I'm looking at the far past limit, the far past sigma algebra by g of minus infinity, and I'm looking at this martingale, which is martingale in the normal indices, which is going to see the proof in a second. It's a martingale in normal indices, but instead of looking forward, I'm looking at this martingale backwards. So I'm going to take larger and larger n's and m of minus n. So I'm looking at this martingale kind of backwards in time, and then the statement is that there is a limit, and this limit can be obtained as the conditional expectation of this L1 random variable I started with, conditioned on the limiting sigma algebra backwards in time. Now, I'd like to take a look at the Uppers theorem, which we did before. The Uppers theorem was looking at an increasing system of sigma algebras. We had a random variable psi, and we conditioned on more and more events we know. So we went into the future with n, with fn. Fn is the natural filtration there. And we conditioned on finer and finer sigma algebras, meaning that we had more and more information about psi. That's how we constructed mn before, and then we looked at the future limit, which was containing essentially all the information we needed about we had about our process, and we proved that the Martingale converge is there. This one kind of goes backwards instead. We're looking at less and less information, and we're trying to find out what can we say about the quantity gamma conditioned on less and less information about our process. Okay, and the statement is that there is a backwards limit as well, and you can essentially swap limit and conditional expectation. Okay, now let me give you a sketch of proof. I'm not going to fully prove it. I'm going to give a sketch of proof. So I'm not going to do all steps, and of course I'm not asking you to memorize all steps, right? First of all, let me show you it's a Martingale. That this is a Martingale is actually very standard. So take a Martingale. MK is a Martingale. It's exactly the same calculation as before, except that I'm using negative k indices. So k is less than or equal to 1, minus 1, because I defined n to be from 1 up, and the Martingale is therefore from minus 1 down. But other than that, it's the same calculation. So how does that go? You look at the expectation of mk plus 1 given gk, and other than k being negative, it's exactly the standard calculation, so nothing special here. What is mk plus 1? Is defined to be the conditional expectation of is defined to be the conditional expectation of, okay, so I need to look at gamma here, and it's a bit confusing what index should I put here, but actually if you look at the definition, all you need to do is just pick this index and put it there. So I'm going to put there g of k plus 1, which is negative, right? Which is negative. Clearly here k should be at least at most minus 2, because I'm defining my martingales and my g is up to minus 1. So at this proof k is less than or equal to minus 2. Okay, so then these things make sense, and I have the conditional expectation for the Martingale here. That's the definition of my Martingale. And I'm looking at the conditional expectation of all of this business given gk. That's what the outer expectation told me to do. Okay, and now what I need to use is that the rougher of these two is gk. So the higher index, the finer we are. So gk is rougher, gk plus 1 is finer. And now I need to refer to the tower rule, saying that the conditional expectations, if you tower them, then they are always simplify. If one sigma algebra is a subset of the other, which is the case here, then they always simplify to the rougher conditional expectation with respect to the rougher sigma algebra. So the tower rule here tells me that this just collapses into the conditional expectation given the rougher of the two, which is gk, and that was my definition for mk. And so the Martingale property is as simple as that. Okay, now that was the first thing to show, that we're talking about martingales. Okay, now if we have martingales, then of course we have a lot of tools available and a lot of methods available to us, most of which we already saw with the uniformly integrable Martingale business. So the next steps are the following. I'm not going to detail all of them. So then prove that M is uniformly integrable. And the proof of that works very similarly to the forward case, to the original uniform integrability proof. Then prove, so then it follows that M is bounded in L1. Okay, once that's known, then you can do the upcrossing proof. You can adjust the upcrossing proof. So adjust to this setting the upcrossing proof. I'm not going to detail this. There was this proof using the upcrossings, and that will show convergence in almost surely. So m of minus n converges to m of some limit m of minus infinity almost surely. Combine that with uniform integrability and boundedness in a, well, just uniform integrability, and you get convergence in L1. Okay, so this is not detailed here, but it follows the procedures we already saw. So I'm not going to explain that further here, but I'd like to still show you the last statement we had, namely that m minus infinity is the conditional expectation with respect to g minus infinity. Let me just repeat that part of the. It's again following the similar arguments that we had before, so it's essentially a repetition. But let me show that to you. Okay, so to show that we have this this equality when we pass to the limit. So to show that m of minus infinity, the limit we had, is actually equal to the expectation of gamma given g infinity minus infinity. Let me detail this a little bit. So this is almost surely, of course. Okay, so fix some r, and we're gonna fix an event g that's in g minus infinity. Okay, and remember that g minus infinity was the intersection of all of the g's. In particular, g minus infinity must be a subset of g minus r, because it's the intersection of all of these g minus r's. Okay, and then let's start looking at the expectation of gamma on g. The expectation of gamma on g. I can do a Taylor rule. Expectation of, and again these steps are similar to those we have seen before. I can condition on g minus r. Okay. G is in g minus r, so actually it can, this indicator is measurable with respect to g minus r. It can go in and out the expectation. So I can do expectation of gamma given g minus r, and I factor out the indicator g. Okay. This is how I defined my martingale. So it's expectation of m of minus r on g. All right, so that's the first observation, and then the second observation is based on this, is that m of minus r, expectation of m of minus r on g will be close to m of minus infinity on g. So let's see how that goes. So also we can do expectation of m of minus r on g minus expectation of m of minus infinity on g. And again, this is not very new. It's kind of similar to arguments we had before. I can factor out the indicator because it's a common factor. So it's expectation of m of minus r minus m of minus infinity under g, all of that under g, which is of course smaller than or equal to the, and I have a mod, which is smaller than or equal to, well, I do two things here. First, I'm going to use a Jensen to bring the mod inside the expectation. So mod is convex, mod of the expectation is smaller than or equal than expectation of the mod. So I bring a mod inside the expectation. That will give me the difference times the indicator mod, which is the mod of the, let's do this. So this is the mod of the m minus r minus m infinity under g. The mod is non-negative. So if I forget about the indicator, which is 0 or 1, then this is further bounded from above by the expectation of m minus r minus m minus infinity. This is a minus, which I know goes to 0 as r goes to infinity by the L1 convergence. by L1 convergence, which I already know. Okay, and that shows that this thing here converges to m minus infinity of g. Okay, so expectation of gamma on g was equal to e m minus r g, which converges as r goes to infinity, almost surely. Well, in L1, let's say L1, converges to m of expectation of m minus infinity on g. Okay, but notice that on the left hand side I don't have an r, and on the right hand side I don't have an r. So it follows that by taking a large enough r, it follows that e of gamma on g is actually equal to e of m minus infinity on g, say almost surely. Okay, and we're done, because what did we want to show? We wanted to show that m minus infinity is the conditional expectation of gamma given g minus infinity. M minus infinity is clearly g minus infinity measurable, because it's a limit of people in g minus r's. Okay, g is an arbitrary subset of g minus infinity at this point, and so what we see is that we are, after this conditional expectation here, we found the g minus infinity measurable random variable, such that for any g in g minus infinity we have this equality. So if you look at Kolmogorov's theorem on conditional expectation, it follows, so thus it follows that m minus infinity is a version of the conditional expectation gamma given g minus infinity. Okay, it's a version, or you could say almost, well, let's say is a version of that. Okay, so it's equal in this sense. Okay, and that's the last bit of proof I wanted to show you. So I didn't prove the whole thing. I left some sketches for showing convergence, but to show that actually you have this conditional expectation of gamma given g minus infinity is in fact your limit, this is done fully here.